Okay, so in this particular session, we'll look at electrodynamics, photoelectric effect. I'm not sure about electrolytic cell because I don't want to rush. But if my aim is to look at it, if we can, good. If we cannot, we'll look at it in the other session. But today, quickly, let's look at electrodynamics. Very short. I'm just going to summarize what we need to know very, very quickly. For some of us, we're still completing syllabus. So I'm putting you, I'm actually putting you as priority, electrodynamics. So I'm going to move fast. Okay. It's just a summary, quick summary. Now, when we talk about electrodynamics, the word electro simply refers to electricity. Dynamic means movement. So we quickly break this into two very fast. When we talk about electro, we talk about what? Electricity. And when we talk about dynamics, we're talking about movement. And when I talk about electricity, I'm referring to electrical energy. About movement, I'm talking about mechanical energy. Now, when I look at this, electrical energy. Now, so when we study electrodynamics, we're talking about how to convert electrical to mechanical and how to convert what? Mechanical back to electrical. And that's the whole story. We want to convert that to that, and we want to convert that to that. If I ask you now, guys, that when there's no electricity, what do we use apart from lamps? We get a generator. What are we trying to produce? Electricity. Now, you would notice when we have a generator, what we need to do, we need to either kickstart or create a movement. So we are converting mechanical to electrical using a generator. Just quickly put load shedding at the back of your mind. That when there's load shedding, what do we need? A generator. To produce what? Electricity. Okay, so from mechanical to electrical, we need a generator. Right? And from electrical, now I should put my generator down. From mechanical here, we have a generator. And here we have a motor. So this is your first 1-2 marks answer that you would give in an exam. What is the energy conversion in a generator? Mechanical to electrical. What about, what will a motor do? A motor would convert electrical to mechanical. Let's look at quick examples of your motor. Quick examples of your motor. You have something like your washing machine at home. What will your washing machine do? So if you take your washing machine at home, what do you need? You need to connect it to what? Electricity. And what happens? It starts moving. Your microwave, your hair dryer, your fan. Now, what is that? Is that a generator or a motor? That's a motor because you are converting electrical to mechanical. So I want you to, look at things at home that can help you remember stuff. Okay? While a generator would convert what? Mechanical to electrical. Quickly. Generators work on the principle. Okay, generators work on the principle called electromagnetic induction. That's the principle. Electromagnetic what? Induction. Principle of electromagnetic induction. This is Faraday's law. While motors simply work on the principle called the Molto effect. I'm trying to compress everything here, so make sure you understand everything I write on the slide. Let me actually write this in yellow. I'll take the pen again. All right. What is this? The principle of Faraday's law. Faraday's law of electromagnetic induction. That's another mark there for you. Principle of Faraday's law of electromagnetic induction. While motors would work on the principle of the Molto effect. So we've covered a few things on this first slide. A generator would convert mechanical to electrical. A motor would convert electrical to mechanical on the principle of Molto effect, while generators work on the principle of electromagnetic what? Induction. It's just a summary I want to put together for you. Now, let's quickly zoom in into a generator very fast. There are two types of generator. But before I even go into two types of generator, please note, what is let's look at electromagnetic induction quickly. What is electromagnetic induction itself? Oh no, I should have actually used my FET to show you a few things. Okay, let me see if I can quickly get my FET Colorado to show you a few demonstrations. It's going to make it easier to deal with. All right, it's going to make it a lot easier to deal with, so that you would remember this very easily. And should you have a laptop at home, you can also play with this. Just check the website. Okay, Faraday's law quickly. All right, Faraday's law, just to explain electromagnetic induction for you. And I'm going to do a whole lot of things here. Just 1 second. One second. Yeah, that's what I need. Sorry for the delay, just to make it a bit more interactive. Okay, so while I'm doing all of this, we're saying a generator would convert what? Mechanical to electrical, while a motor would do the opposite. Generators work on the principle called the Molto effect, while motors work on the principle called the Molto effect, right? Lovely. Now, there are two types of generator. But before I jump into those two types of generator, it is important to understand what electromagnetic induction is. Okay, this thing is now taking its own time. Let me see if I run the Java version. I hope it works. Sorry for the delay. Oh, sweet, it works. Lovely. Now, I want to quickly look at electromagnetic what? Induction. I'm going to come back to that, because I want you to understand this and enjoy the whole topic very fast. Electromagnetic what? Induction. The word induction, induced. Induced means to produce. To produce what is not there. All right? Induced means we produce what is not there. So when we say electromagnetic, there are two words I want you to see there. What word do you see? I see electricity, and I see what? Magnet. it means we can generate electricity using a magnet. So electromagnetic induction is the relative movement, all right, between a coil and a magnet, which creates a change in the magnetic flux. This change induces, we did this in grade 11, induces current. And we use this formula, negative delta phi over delta t. We're not going to calculate with that formula, but it's going to help us understand a whole lot of things. And the key thing is, guys, there must be movement. I'm going to do this simulation. I want you to remember it must be a picture in your mind. That's why I want to use the simulation to cut out a lot of theories. You remember what you see more. Okay? So anytime you have a magnet and you have a coil, if you move them, you are going to generate what? Electricity. By what? By the change in the magnetic flux. Okay? So I'm going to run to my simulation now and show you something. Oh, by the way, I want you to write this. This electromagnetic induction, very important. This electromagnetic induction always, please take note, I'm going to dwell on this a little bit, always produces alternating. And when I say alternating, alternating means to change. Alternating what? Current. It will always produce what? Alternating current. Current that changes in every direction. Current that changes in every what? Direction. Alternate means to change. And I want to just demonstrate that to you. And we're still going to look at what alternating current is. Current that changes in every cycle. At one time it becomes positive, at the other. We mentioned this, if you remember, under electrolysis, where we say we don't use alternating current. We use what? Direct. Okay. So it's a connection. Let me run, because of time now, and quickly show you. Now, what do I have? I want you to check this quickly. I've got a magnet. I want to do that. No. Check this. I've got a magnet. Is that okay? My magnet, you will see North and South Pole. Or let me do this before I do that. Yeah, let's work with this. I've got a magnet. And what I have here, you see this wire, we call it loop of wire. It's a coil. And you would see we have a light bulb. The light bulb is to check if we are really going to produce what? Electricity. And all I'm going to do is to move my magnet. That's all. Once I move a magnet, that's why we say the movement of what? A magnet relative to a coil. Once you have that movement, check again. Do you see that? Is there a battery here? No. I want you to notice something. Check this. I want you to notice the direction of that arrow. That's a galvanometer to show us the direction. What do you notice? That at one point it's positive, and at the other point it is what? Negative. That's your alternating. Done. Means it keeps changing direction, positive, and that's why the bulb will continue to, you see, it glows, goes off, it glows, that is alternating what? Current. I want us to learn a few things, and I'm going to ask you a few questions. This is what we talk about when we say hydroelectric power. When we use, some of you think that we are using water to really create electricity. Don't be deceived. Water does not create electricity. All right? Water just allows this magnet to rotate there. So when there is water decrease I remember there was a time where there was water. Some of you think, oh, is it not raining? Can't we not put water in a bucket and put wire and generate electricity? No. Water only causes what? A creation. Let me use this. I don't know if you see the alternating. Do you see it? One time it's positive, and the other time it's what? Negative. Positive. You see? That is alter. This is simple electromagnetic what? Induction. It will always generate alternating current. Because I'm going to go somewhere when I draw diagrams now, and I don't want you to be confused. But let's see. I want us to quickly use this to discuss a few things. Look at my formula that I wrote here. E equals to what? Negative N delta phi over what? Delta T. That's a grade 11 formula. And I want us to quickly look at it. E equals to negative N, change in phi over change in time. This is my induced what? EMF. I'm sure we remember that when we're doing circuits. Because we can use that to say V equals to IR, if you remember. All right? V, we can calculate current there. Now, what is N? N is the number of turns of wire, or which we call the loop. T is the time of rotation. And this is the change in magnetic flux. And I'll quickly tell you this. The change in magnetic flux quickly talks about the strength of the magnet. I want us to do a bit of mathematics here. Simple maths. How would you increase the value of E? Aim to increase the value of E. What would you do? Simple maths. No, we want to increase the value of E. We're not solving for E. Good. Time must decrease. Time decreases, E is going to increase. And if time decreases, you know what that means? It means we increase the speed of rotation. Increase the speed of, I'm going to quickly go back to my simulation and let's do this. If we increase the speed, what happens? Check this. Look at how fast my turbine is moving. Do you see? Let's use the light bulb. Do you see how bright this light bulb is? Should I increase the speed? What happens? It's brighter. We're done. Examiners are going to ask you, how do you increase the amount of what? Current generated. What do? We increase the speed of rotation. Are we okay there? Let's explore that before we look at the second one. We increase the speed of rotation. I want to do something on this speed of rotation. We talk about the speed of rotation. I'm going to quickly do something, guys. You should all have done this, so I'm just summarizing here and quickly filling loopholes. It's an alternating. We said at a point in time, it will be what? Positive, then it becomes what? Negative, then it goes back to what? Positive, then it goes back to what? Negative. This looks like a graph. All right, so this is induced EMF, and this is what? Time. I wanted to check, please, I wanted to follow this. Just rush in and look at other stuff. This is one complete what? Cycle. One what? Cycle. One cycle. Now, if I were to increase the speed, one cycle, and this is time. If I were to increase the speed, what does that mean? It means that it is possible. Let's say I double the speed. It means I will, number one, increase the amount of current I produce, like we saw. However, check this. The revolution will change. I don't know if you see what I've just done. In the same cycle, what have I done? I have moved twice. It means I have got how many rotations here? 2 rotations. I don't know if that makes sense. Because here is the normal speed I was using. That's my normal speed. 1. But if I double the speed, I am going to go twice in 1. When you see this, please understand that the speed of rotation has changed. Is that okay? The speed of what? Rotation has changed. And that's why we have what? A higher EMF. Let's call this EMF 2, and let's call this EMF what? 1. So, EMF has increased. Why? The speed of rotation has what? Changed. It has increased. Make sense, everybody? All right. What do you think I would do again? That's number 1. To increase E, number 1. What do you think I'll do again, number 2? Look at the formula. Let's do maths. Increase N. Increase the number of what? Turns. Let's go demonstrate it quickly. Increase the number of turns of Y. So just remembering that formula makes things work. Let's go. How many loop of wires do we have? 2. Let me make it 3. What do you notice? I don't know if you see that it's gone brighter. Let me make it very clear. That's 1. You see, I didn't change the speed right now. I left the speed constant. What am I doing now? I am changing the loops. Make sense? So the more the number of turns, the bigger what? The current. Is that okay? Now check this. This will not affect my graph. It has nothing to do with it. How would we draw the graph here? This is speed of rotation, right? If I increase the number of turns, let's go check what our graph would look like. So, increasing what? N. What will my graph look like? It's important to know all of these little details. All right, this is the original again. Okay, let's make it 2. Sine graph. Okay, that is E1. E1. What do you think E2 would look like if I increase N? One thing I'm sure of is that what? The current will what? Increase. But what happens to your speed of rotation? Are we changing it? No. It means my cycle still remains what? The same. Check what the graph would look like. I don't know if this compared to the other one makes sense to you. Okay, I missed somewhere there. This just goes up. If you still do your trigs, this is basically saying sine x and sine 2x. The amplitude has increased, but the period remains what? The same. I hope it makes sense. So when you see a graph, you must know what the examiner has done. Here, what have we done? We have increased what? N. Here, what have we done? We have increased the speed because we have a double what? Revolution. Does that make sense to you? Okay, look at number 3. 3. You see this delta phi? It's changing magnetic flux. If this value increases, this one will also what? Increase. So I'm going to say use a stronger magnet. Use a stronger what? Magnet. So if I were to take you back to maths, just for some of you to understand, this would be what? Sine x. What will this one be? Sine 2x. Make sense? Period has become, period here is what? 360. What is the period here? 180. This one is what? Sine x. What is this one? 2 sine x. Increase in, just to make you remember, since we did a lot of tricks in maths. 2 sine x. All right. So number 3, I said we should change what? The magnet. Use a stronger what? Magnet. Let's go check. On my right-hand side, I can change the strength. What do you notice? The strength of the magnet right now, if you can see from your screen, is 9%. That's how strong the magnet is. Okay? Remember, this is a simulation that helps us change a lot of things. What if I increase the strength of the magnet? Let's go to 50. I'm using a stronger magnet now. What happens to the brighter? Let's go to 100. What happens? Do you understand that? Those are 3 important things that you must know that will affect what? Now, wait. Did I change my speed of rotation? No. It means that this graph still works. Stronger what? Magnet. Stronger magnet. Are we okay? All right. Sweet. Let's quickly go to the difference between AC and a DC. AC and what? DC. What does AC mean? AC means alternating current. What about DC? Direct. All right, alternating current changes direction every half cycle. Here, single direction. And that's why your graph here would look like a sine graph that we've been talking about. Changes direction. And here, maintains a single direction in every half cycle. Current flows in one direction. You see, it's always positive there. All right, so we could have current here, or EMF, and we have time. Current. And remember, what causes alternating current? Electromagnetic induction. Anytime there's electromagnetic induction, relative movement between what? A magnet and a coil, we would always generate alternating current. There are a few advantages that you need to know. Just summarizing, like I said, advantages of AC over DC. Then we look at the makeup of the generators. Advantages of AC over DC. I'm going to talk about 4 or 5 of them. Advantages of AC over DC. So this is a reminder, and if you are, for those of you that have not yet completed this, just flow. Okay? Advantages of AC over DC. Okay, quick one. Let's create this. Okay, no, there's no need. Let me do this. AC. Advantages of AC over DC. After this, we'll look at the parts of a generator, and then we go answer some questions. Whatever I've not answered, I've not spoken about, we'll deal with it when we answer a question. Number 1, AC can be easily stepped up or down using a transformer. So when you see transformers, don't think that they're just there for fun. What they are doing is they are helping us to reduce the current that comes into our houses. All right? Because from the power station, it's a lot. If you say you are tired of load shedding, you want to go and connect your house directly to Eskom power station, good luck. Yeah, it will sacrifice of praise. All right? So the transformers from the main source goes into a station, it is reduced, goes into a substation, it is reduced, goes into another substation, it is reduced, gets into your transformer, it is reduced, because you only need like 220 at home. So it goes into all of those. If you, for example, in the UK, they use 110. We use 220 here. If you buy a TV from the UK and bring it here, it's going to explode. Because the UK TV is made to function under 110, while ours is what? 220. There's an adapter that you must put there to step it down. Check your phone batteries. Your phone charger battery is what? 3.7 volts. 3.7 somewhere there. Now you are plugging it into a 220. If you want to check if what I'm saying is true, it's very easy. You can do it today at home. Cut the head of your charger. Make sure you only have the cable and plug it in. Good if it's an iPhone 14. And check, since you're all bragging about iPhones, plug it in. I'm using an Android. I know that we don't play with electricity. But since you said, sorry for all the iPhone users. And number 2, AC can easily be stepped up or stepped down, right? Number 2, AC can be converted easily to DC. This is very important. AC can be easily converted by using a split ring commutator. Most of the devices in our houses use DC. And I'm going to go back to this point later. AC can be converted easily to DC by using what? A split ring commutator. Number 3, AC can be transported. Don't think they use a vehicle, please. Can be transported. Say, it's a taxi. Can be transported over long distances with high voltage and low current to reduce loss due to heat. If you remember grade 10, we said it cannot be created or destroyed but transformed from one form to another. Sure, look, an easy way that I use to remember this is this. I don't know if you walked past some places where there's electricity substation, they normally write something there. They say, danger, Ingos. What did they write? Danger, Ingozi, which other word? Kefar. Khafar, that's Afrikaans. Khafar. Wait, they write something there as well. I want to show you how to remember this. After writing danger, what do they write? High voltage. They say high voltage. All right. So we say high voltage, so it helps in reducing what? Heat loss. That you would have done under electric circuit when you were calculating energy. All right, so please take note, high voltage. And number 4, I'll give you one more. AC is cheaper to produce. It's cheaper because you only need a magnet and a coil. That's all. Nothing else. With a DC, you still need a split ring commutator. With AC, we don't need anything. Just take a magnet and move it through a coil. You have already produced what? AC. Very easy to produce. So advantages of AC, please know at least 2 of them for an exam. You will be tested. Minimum is 2. Now, quickly going to look at the difference between AC and a DC generator. AC generator and a DC. There's only one difference there. Split ring commutator and slip rings. I think I've got a diagram there. Yep. Let us quickly, on this diagram, look at the functions of this and look at the difference between that. Okay, good. Your alternator in your car is actually a generator. The alternator in the car. That's why people who have bad alternators keep pushing their cars. Why? It's not charging. So the alternator, as the car moves, what happens? It converts the mechanical to electric. I remember when in school we used to start about 5 cars with 1 battery. Just start it, remove the battery, because that's the only thing the battery does. It's just to start the car. Otherwise, it's useless. Start, transfer. That one keeps running as long as it doesn't go off. Move into another one. Start again. Move into another. And that's it. As the car then moves, it generates what? Its own electrical energy by converting mechanical to electrical, because your radio must keep working without a battery. All right, the lights. So all those come from an alternator in the car. Now, let's quickly look at all the... here you might just need to take a picture when we're done. What will a magnet do? Function of a magnet is to produce the magnetic field. A magnet will produce what? Magnetic field. Let's look at this. A commutator, what will it do? It allows current to flow in one direction in both halves of the cycle. So this is what converts, and I want to quickly say something here. We said it is easy to convert AC to what? DC. Please look up here, everybody. When we take this coil, what we are doing with this coil is we are rotating. We are rotating the coil. Is that okay? Wait, there's a coil here, which is also called an armature, and there's a magnet. Anytime you rotate a coil through a magnet, what do you produce? I want us to be very specific now. We induce current. What type of current are we inducing? You listen to the question. This whole process is called electromagnetic what? Induction. But anytime we rotate a magnet through a coil, we produce a type of current. What is that current? It's alternating. Every time. It means right here, I want you to understand this whole thing. Right here in the coil, what are we generating? We generate what? AC. We generate. We generate what? AC. But what changes the AC into AC? Your split ring commutator. I don't know if it makes sense. So here as well, what do we generate? We generate what? AC. So what is the function here of the split rings? Oh, it keeps current flowing. All right? In different what? Directions. In different halves. So you would see that we would have one half of the cycle, the other half of the cycle. It keeps, because current is already, the movement has already produced what? AC. It just keeps it that way. While in direct, what happens? We produce AC, but the split ring does what? Changes it into what? DC direct current. This is called a split ring commutator. And it's very easy. Means, baby, you were not listening to me. Wait, let's go back. That's why I said I mentioned it earlier on, and I wanted to go back. The electromagnetic induction always does what? Produce what? Alternate. I wanted to put the sequence. Is that fine with you? Anytime we move a magnet through a coil, what are we generating? Alternating. Anytime you move a coil through a magnet, we alternating. We okay there? Point number 2. Check my point number 2. Point number 2. I wanted to see something. AC number 2 can be converted easily to DC by using what? A split ring. Which means here, what are we generating? AC. Only when it comes out here, it becomes DC. So the conversion takes place here. But you get it now. So with a DC generator, we're actually having two types of AC in the coil, DC outside. With an AC, it is AC. We keep it. We maintain it. Make sense? All right. So it's a very tricky one. I came across questions like that, so I always just mention it. So an examiner will give you a DC generator and ask you which type of current is produced in the coil. Your head is thinking, oh, it's a DC generator, so it's DC, already minus 1 over 150. Yeah. But are you okay now? That here, it is AC. Then we convert it with, this is your converter. All right. One more thing here, quickly, is what is the function of a carbon brush? Carbon brush. Now, you would notice your rings are connected to a carbon brush. All right? Okay, I've got a question. So what's the difference if you say it's an induced current and an AC? Oh, no. When we say induced, it means it's created. AC now is the type of current that we create. So we induce an AC current. Klubikazi. I don't know if that makes sense. AC is the type, either AC or DC, but it's just current. So we induce an AC current. Let me know if you're okay. What is the function of the carbon brush? All right. It connects. Why do I have that? I want us to go answer a few questions now. And then we do calculations when we answer a question, right? It connects let me say allows current to flow. Oops. All right. It allows or connects the current in the coil. Allows current in the coil, all right, to flow to the external circuit. Where's my external? That is my external. We call it external or we call it load. So the only thing is just that it's a connector. That's all. If we don't put a connector there, then wires are going to be all over the place, and it's just a design. And we use carbon because carbon is a semiconductor. That's why we call it graphite. Again, we come back to it in electrodynamics. So a carbon brush allows current or connects the current in the coil to, okay, I'll put this here, to the external what? Circuit. So please be able to identify. Here you are going to have what? 2 slip rings. I want you to see 2 slip rings. If you take a split ring and break it into 2, it becomes half. What are you doing? Splitting it. That's where the name comes from. Make sense? There's a funny thing I like to do. Check this. If you get confused, simple. If I have a circle here and I split this, do you know I've already written 2 letters? I've written DC. If you split that, you have written D and C, because if you connect your C and your D, you form a circle. So just split it and you remember. So anytime you're confused, know that, okay, how do I get DC? I've got to split a ring or a circle. Hence the name what? Split ring. But please, what's mostly important is to mention what? Commutator. Let's go play around with a few questions. I'm sure I've been able to answer a few things. Oh, I just remember what I need to talk about RMS. Okay, sir, is there any other function for carbon brush like holding the rings in position? Okay, those are just the primary, that's a secondary function. But the primary aim is that it allows current, it serves as a conduit for current to flow, not really to hold it in position. Okay. Let me define one thing that learners always forget. And just need to talk about this quickly, and then we move on. Ooh, 2 things. I thought I was just going to answer questions today. RMS, voltage, or current. What does RMS mean? It means the root mean square. Root mean square. Now, what does this mean? We define this. So an examiner will ask you for either RMS voltage or RMS current. It's the same definition. So I'll say RMS voltage or current. So in case they ask you for current, you stick to current. If they ask you for voltage, you stick to voltage. All right? Is the AC voltage or current, so if they ask for voltage, continue with voltage, right? That produces the same power as a DC voltage or current. It starts from A to D alphabetically. All right? Except you are doing politics. That's when you say DA. But alphabetically, it's A to D. That's what I use in remembering all the time. I start from A and I go to D. It is the AC voltage that produces the same power. Some would say the AC voltage that has the same heating effect. They are all the same story. Produces the same power as this. So please, we're going to use formulas to work that out. And these are free marks when it comes to calculation. I'm going to show you how to calculate. Just use your formula page. Now, on a graph, where is your RMS voltage? Oh no, why? On a graph, where is your RMS? Your RMS current or voltage is always smaller. All right, this is, if this is I, this becomes my IRMS. And this point is known as my I or I peak current. So check where your IRMS is. They will always use graphs sometimes to want to deceive us. Oh, finally. I keep saying finally. But I don't want to miss any point. I just want to explain this in a very, very funny way so that you remember. Okay? RMS voltage and current. Okay. Last thing, then I look at the question. Last thing, I promise. Last thing. It is the last. You would see. Just that I don't like answering questions when talking about the concept when I see a question. I want to deal with all the concepts. Oh, it's not the last. God, I just remembered again. Okay. No, it's because of you guys. Okay. The position of the coil. Position of the coil. I'll use a graph to talk about all of this. Position of the coil. The position of the coil. All right. So the yellow is just my coil. Remember, it's rotating. Okay? It keeps rotating. The position of the coil. This will be 0. This will be what? 90. This will be 180, 270, and what? 360. Now, anytime your coil is vertical, I want you to check something. Do you notice that whenever the coil is vertical, we're generating 0? Every time it's vertical, we have 0 current produced. Do you see that? 0. What does that mean? So coil is vertical. What does it mean? Here, we're generating what? Maximum. While coil is what? Horizontal. I quickly want to deal with the vertical and the horizontal stuff. Just I don't want you to cram it as vertical. Examiners can be tricky. Okay, when we have this, no. When we have this and we have this, what does it mean? Here, the surface of the coil is parallel to the magnetic field and perpendicular to the normal. I wanted to check something here. If I were to draw a normal here, what do you notice? 90 degrees. That's when we generate what? Maximum. But here, the surface of the coil is perpendicular to the magnetic field. I'll try to draw the magnetic field as well. To the magnetic field, not filed, field, and it is parallel to the normal. Parallel to the normal means 0. So that is our magnetic field. Let me use a green one. Magnetic field from the North Pole to the South Pole. So when we say the surface of the coil, the yellow line, is perpendicular to the magnetic field. Perpendicular, do you see that? And parallel to the normal. Remember, I was using dotted lines for normal. What are we generating? 0. But when the surface of the coil is parallel to the magnetic field, you know, I always use a funny way to explain this. Let me try to, for those online, to make this look very, very, a picture. Is that okay? A picture. If I wish I could draw. I wish I could draw. If I have a guy here, okay, let's draw a guy. This is how we used to draw guys when. All right, this is how we used to draw guys when I was in school. We have a guy there, and we have the ear there. A cute boy, and I have a lady with long hair. The guy looks like an Asian. Okay. There's some affinity for Asians here. Okay. And we've got a beautiful girl with lovely earrings there. Okay. Now, I know that women are moved by what they hear, and that's why a girl would keep listening to a guy who's lying. Okay. And men are moved by what they see. It's just natural. That's how we're made. And that's why if you get to the mall, it is men that keep turning their heads. Makes sense? All right, check this. I want us to quickly draw. Listen, I want us to draw the love meter between the two of them. This guy is going to be my north pole of the magnet because love would move from the north to the south. Okay? Now, but check what I have in between them. I've got a pillar. I've got a pillar. Shame. All right. So the guy cannot see the girl. The girl cannot hear the guy. Men are moved by what they see. Women are moved by what they hear. At this particular position, is there any love generated? Huh? No, there's no love generated. Because cannot see. Remember, this is what generates the love. Make sense? So, are we generating anything? 0. But as this thing begins to rotate, that's what you call mechanical. Let's move the pillar. Oh, there's a bit of, I can see her hair. Sound can travel a little bit better. What's happening to the love? It's growing. The love is growing. All right? What happens? Maximum love. Oh, you are the only COVID in my life. You are the only vaccination I'm going to receive. Blah, 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 blah. The only what not, and what not. Maximum love here. All right? Why? Do you notice that the magnetic field is now parallel to my coil? All right? And then what happens? Yes, you have a question, Manny? We go again. We go again. What happens? Back to 0. Because we are rotating. Right? Question? Induced? It's the same. When we say induced EMF, inducing EMF when we induce current, because we can always convert that. E equals to what? I. So when we talk about induced current, induced EMF, we really mean we induce current, but we can calculate the EMF. It's the same concept. Okay. So guys, I hope it's making sense. See, you guys are online. It's just the love thing. It's a love thing. It's a love thing. It's a love thing. Woo! Maximum. 0. Growing. Maximum. 0. Make sense? So I hope you remember that. If you don't want to remember, just find somebody, fall in love with them quickly before exam. Just All right. And then check them. No, there's no maximum. When there's an invigilator blocking you, you are angry. This invigilator must just move. Makes sense? Because blocking you. Look, I hope it makes sense. Let's answer some questions quickly and just, guys, that's how I just use all of these things to remember a few things. Oh, okay. All right. So, that is a generator. One more thing. One more thing. How do you detect the direction of motion of a generator? I'm going to do that together with a motor. All right? We spoke about a motor already. What will a motor do? A motor would convert what? Electrical to mechanical, using the principle of motor effect. Now, what happens with a motor is this. With a generator, we don't have a power supply because we are producing what? Electricity. But with a motor, we are going to have what? A power supply. To quickly see the difference here. But the issue of the DC, and it remains the same there. Do you notice there's a power supply here? Power what? Supply. That's what makes it a motor. Because we connect to electricity and then it moves. This one is what? A generator. Because we are mechanically moving stuff. Can you see axis of rotation? This is mechanical to electrical. Now, this is what the examiners are going to ask you. We spoke about how to increase the current in a generator. If you remember the three things we spoke about. Number one, increase the speed of what? Rotation. Number two, use a stronger magnet. Number three, increase the number of turns. Now, because we are producing what? Electricity. What about a motor? Examiners will ask you how, they're not going to ask you how you produce electricity in a motor. No. How do you increase the speed of rotation? Because that's what we're doing with a motor. You have your fan, your hair dryer at home. There's levels. Level 1, level 2. Level 1 to blow small. Level 2, you want it to blow the hair. I don't know how you all copy those. Then number but just blowing your hair with hot stuff. But it's okay. If I were to come back to this world, I'll come like a guy. Leave my hair for 1 year, not even cut it. But you must go salon every 2 weeks. Your hair is 350 once. That 350 covers me for 6 months. So nice. All right. How to increase the speed in a motor. But I've just simply summarized a whole topic to you. How to increase the speed in a motor. Number one, increase. I'm just going to summarize. Increase N. Number two, stronger what? Magnet. To remain the same for both of them. Use a stronger magnet. And number three is where they are different. All right, increase current. Remember, a motor, we are using current. Is that okay? So if you want the motor to move faster, what do? Increase what? Current. So that's what you keep doing when you change and it blows. It's just that. So when you change from 1 to 2, you are changing resistance to affect what? Current. So they're connected. Okay. With that done, but almost done, the last thing I'm going to do, Klubikazi, you were enjoying the lesson. Sweet. All right, I'm glad, and I hope it's making sense. For those of you that have done the topic, I hope you're just putting up, closing all the gaps. Okay? Now, with me, there's something I know that it's my story of my life. Okay? The story of my life is this, that God rules And I'm saying my life, you're talking about the world. God, God rules my life. Very, very easy. That's just my motto. God rules my life. But basically, you know what I'm telling you? I am telling you that it's G, R, M, and L. Basically, I'm saying for generators, we use the right hand. And for motors, we use what? We use the left hand. Generators, we use right hand. And motors, we use what? Left hand. I hope you remember that quickly. God rules my life. All right. Yeah, God rules my life. So generators, we use right. And motors, we use left. I've got a picture somewhere that since I cannot do this, I wish I could do this with you all physically for you to see. It's 1 mark here, but we can waste 10 minutes on this. But I don't want that to happen. Where are we? All right, and that's it, guys. So you would see there that I normally, this is current. Is that okay? This is field. Okay, wait, that I'm writing FC. What are you thinking of? KFC. Aha, I knew it. Okay, I knew it, KFC. Okay, again, C. At least that will help you remember. Now, but instead of thinking of K, I just think about motion, MFC, Man City Football Club. If you're a Man City fan, you'll love this. Okay, so a Man City fan. And I love black American movies. These guys are the ones that teach this thing nicely. Every time they talk. You know what I'm saying, man? They just, yeah, you know what I'm saying? Guys, they always give us that hand. You know what I'm saying? Yeah. So they should become teachers. Now, all you need to do, guys, is to place this. Don't forget, we are using, the left is on the left right now. What are we measuring here? What are we checking? Motors. And what are we checking here? Generators. And all you need to do is to place your hand around it. I think I have got a few ones. And I'm done. Okay. Let's answer a few questions together to make life very easy for us so that we practice all of this. Guys, I am done summarizing. If there's any other thing, I'll add. But all the concepts have just been summarized here. If there's anything, I'll add. Okay, let's check this. The following information on a household electrical appliance, please let's check, is 230 volts and 500 watts. Hold on. Here I'm going to use formulas to answer this. 230 volts and 500 watts. When we say 500 watts, what are we talking about? Power. Right? Watt is the unit of power. Okay. I'm glad, Bibi, you're not answering me because I'm not asking. I am telling, what is the unit of power? You're still saying what? It's not what I'm telling you. Okay, you get the joke. Now, if I go, please listen. If I go to my formula page, okay, there's someone's mic that is on, and we can hear the whole house. What I had photoelectric effect, that will be in the next class. Please check this. Check how I'm going to respond to this question. Where's my formula for power? Where is it? P average equals to what? V what? RMS. I want you to see where I'm going. And what? Do you notice that RMS goes along with what? Power. I am done with that multiple choice. Check. I want us to read, and then you give me an answer. Please, I need you. It says, the following information is given. We have power right now. The value of 230 volt refers to, so what's my formula? We said P what? Average equals to what? I RMS multiplied by V RMS. Do you think the voltage talks about the peak? No. Average value of the voltage? No. Check C. RMS. Done. No need to cry. Power average is IRMS times what? VRMS. So anytime you see power, it is associated with what? Root mean square. RMS voltage. So please use your formula page. Learn how to use the formula page to get your answer. My correct answer is what? RMS what? Voltage. Remember we defined RMS. It is the AC voltage that generates the same what? Power. Done. 2 marks in the bag. Now we can go work for ESCOM. Just because we can answer that. Already we are applicants. Ooh, check this one. Love this one. This one should remind you of something here. Talks about what? The speed has changed. In the graph below, the solid graph shows the EMF produced by a simple generator varies with time. How? The dashed curve is the output from the same generator after a change was made. What change was made? Let's go check. What change was made to the generator? The speed of the rotation was doubled? The split ring commutator was added? No. If we add a split ring, we are changing from AC to DC. Oh, what should your answer be for B? Your graph should look like this. Make sense? The number of turns in the coil was quadrupled. Means the number of turns was what? Increased. If it was increased, what should your graph look like? If this is my original one, then this one should go up by 4. Make sense? But the number of rotations should still remain what? The same. The strength of the magnet was halved. Oh no. If the strength of the magnet was halved, what are we going to have? The magnitude, or the amplitude rather, will what? Decrease. So if this is the original one, what are we going to have for the new one? It should have, but that the wavelength should still remain what? The same. So what's the correct answer? Let's check. Already you are now the manager of ESCOM, taking away all our load shedding. You see? Okay, no, this one is photoelectric effect. Check this. The diagram shows a simple what? Electric motor. Please don't brrr. No. Motor. There's something I thought I used to use some years ago. We all play games on our phone. Once in a while when we're bored. Okay. Your phone. Okay, when you play a game, you know those games like Candy. There was a time I hated those Candy Crush. Everybody invited me. Candy Crush. You know those Candy Crush? Yeah. Do you know you never start from the same, from the beginning? It stores wherever you stop. Whenever you go back, you start again. So your game has a memory. Oh, I'm done. Check something. It has what? Game memory. Let me have some fun now. This is my time to create some fun. Now, let me actually do it on a different page. Some fun stuff. Fun stuff. Let's call this fun stuff. Fun time. What? Memory. Wait. Some fun time. Yay. Okay. Sweet. Game memory. If you want to write the short form for game, you know I can just say game. You know how we write those funny WhatsApp messages? HUD, WUD, LOL. Come on, this generation is just something else. We normally write in full. Okay, let's join your generation. Game memory. you know what I've done? Generators will convert mechanical to electrical. Motors will convert what? Electrical to mechanical. I'm done. Make sense? Generators will convert mechanical to electrical. Motors. So game what? Memory. Gen, mech, elect, motor, elect, and mechanical. Oh, we are in summer right now, guys. And, okay, check me. After your exams, I'm going to rest in a 5-star hotel in Dubai. Okay, if you want to come along, just let me know. Start buying your tickets. Don't think I'm buying tickets for you. Okay, all right, please. We're going to Dubai. If you are interested, just hit me up on WhatsApp, 0817442103, and I can book a hotel for you. Hotel is in my name, so I'm booking up for you. But flight is on you. Check now. I'm in Dubai. It's hot. What am I going to do? I'm going to sleep with the air condition on. Right? Because I want to make the room cool. Okay, you refuse to go. I'm going to send you a WhatsApp message saying, whoo, it's nice here. And when I sleep at night, I sleep with, I'm writing WhatsApp, right? With what? The AC on. I don't know if you see what I've just done. Slip rings, AC generator. Make sense? When you see slip rings, you're talking about what? Alternating currents. So I sleep with AC on. Done. Simple ways to remember stuff. Fun time over. Okay, let's go answer questions. I have an electric motor. What conversion takes place in the motor? Motor. Electrical to mechanical. Yes, baby. Yay! Electrical to mechanic. I was just making sure that you are mechanical energy. Please put the word energy. Don't just 1 mark. What type of electric motor is illustrated in the diagram? Is it AC or DC? Check the diagram. Check here. It's half. So it has been split. And when it's split, it is what? DC. Give a reason for your answer. Oh, simple. We have what? A split ring commutator. Imagine. Already you have 2 marks. DC, commutator. 2 marks. Guys, I hope it's making sense. So you check there. That's a split ring commutator. Explain the function of the carbon brushes. Oh, I think we did. What? It allows current to move from the coil to the what? External circuit. All right? Allows current to move from, all right. Allows current to move from, let me put the word allow. From what? From the coil to the what? But this time around, current is because it's a motor. All right? It's a motor. What are we doing? Current to move, allows current to move from what? The external to the coil. I don't know if you understand what I just said. Because it's a motor, we have a power supply. So current is going into, because we are converting electrical to, if it's a generator, what happens? It allows current to move from the coil to the external. Make sense? Remember, motor, we are converting electrical to mechanical. Okay, guys, I hope we're good. Oh, to which terminal of the power source is the brush labeled P connected? 1 mark. To which terminal of the power source is the brush connected? All right? If the coil rotates what? Clockwise. Okay, check. What are we doing? We are using our right hand or left hand rule. Which one are we using here? Motors? Motors? God rules my life. Generators, right? Motors, left. All right. Look, I wanted to see how this thing can be done so easily. In fact, because I don't want to switch on my camera, just going to do this for you. This is what you do. Let me see if I can get an answer here using that. Watch this. All right, sweet. Basically, do you see it's quite similar? Is it quite similar? Let's see. I'm using my left-hand rule, right? So the first thing I'm going to look, examiners would give you two things. They will always give you two. You look for the third one. Check the first thing they gave me. North Pole and South Pole. We always point to the south. Makes sense? I'm pointing to the south. Number two, they told me it is moving what? Which means I am pushing up from this side. So your coil is flat, right? When you push up, it flips to the right as if it's moving clockwise. Okay? Now, do you see where the current is coming through? Current is coming here. By this finger. Make sense? Bonga look lost. Left-hand rule. North to south, I'm pointing. We are told it's moving clockwise. The coil is moving clockwise. It's going this way, which means I'm pushing the coil up. Now, if you do this, your third finger would definitely be pointing out. It means current is coming this way. Make sense? That's how current flows. Are we together? All right. But we know this is what? A power supply. It means current is leaving this place. Because, check, you need current to go in. You need to maintain the flow. Do you see that? Oh, sweet. Where would current leave? Current would leave the positive and return to the negative. So my P is negative. I hope it makes sense, everybody. I wish I could switch on my camera to just make it easy, but just use your hand. Use your left hand. Okay? They will give you two. They gave us two here. They gave me north to south. I am pointing to the north and the south. It is moving clockwise. Okay? So my thumb is pointing up. If it was moving anti-clockwise, I'll be doing... But it's moving clockwise. So it means current is coming out like that. For current to come out, it must be coming in there, going there, going there. And we know from electric, that's positive, and that's what? Negative. Conventional current will always move from the positive to the negative. So P is negative. Make sense? Okay, I've got 5 minutes, and let's see if we can answer. Name and explain the basic principle on which a motor works. Which principle does a motor use? Motor what? Effect. Let's quickly explain how it works. I did explain electromagnetic induction, right? Let me go back and explain how a motor works right here. Let me put a note here. What is a motor effect? How does it work? All right. A current carrying wire through a magnetic field experiences a force which causes it to rotate. And that's done. That's the motor effect. So you have a wire, all right, that has electricity. Once you put it in a magnetic field, it experiences a force, and that force is what causes rotation. Please take note of that. That's the motor effect. A current carrying wire through a magnetic field will experience a force. I'll give you a moment to write that down on the Motto effect. A current wire through a magnetic field experiences a force which causes it to rotate. That's why it will rotate when you have a motor. So this is why your hair dryer would rotate, your egg mixer, your washing machine, your microwave. Right? Good. Because once you plug in it into power, current flows into the coil, and there's a magnet there. Automatically, the coil will what? Rotate. So the coil will rotate. It will keep. I told you I'm going to Dubai. From Dubai, I'm going to India. India. I'm going to teach generators and motors. I'm going for a class there. No. I'll be teaching them because I'll be teaching them how to rotate the coil. So you rotate and you keep rotating. And if you want the coil to rotate faster, you got to increase the current in the coil. And then it will rotate and rotate. And then I keep shaking my head. It will keep rotating and rotating. All right. Okay. Let's finish here and just deal with the calculation. Oh, the calculations are always very easy. It's something you should get. Just use the formula page. An electrical appliance with a power rating of 2,000. Guys, I want you to learn to do calculations and physics by writing the things that you have. Write the things that you have, go to the formula page, look for the appropriate formula, substitute. I want you to see how we're going to get, check, 9 marks. This you can do without anyone teaching you. What do we have? Power. It's connected to what? A 230 volt RMS. Do you remember the multiple choice we answered? Do you notice that this is the answer to it now? Confirming that the household produces what? VRMS. That was the multiple choice. All right, let's write the things we have. What do we have? We have power. What's my power? 2,000 watts. Okay, so P is 2,000 what? Watt. What else do we have? VRMS is what? 230 volt. I want you to enjoy science. What are you looking for? You are looking for peak what? Okay, so we are looking for V max. Let's go to a formula page. We don't know that. Let's go and look for a formula. Guys, okay, all of you should have a formula page right now. And you should be checking the formula. Let's see, where's my own formula page? There we go. I don't know if you see a formula already. Do you see a formula? What do we have? We have power. Is that okay? We have what? VRMS. What are we looking for? Vmax. Let's check anywhere we have Vmax here. This is the first formula with a Vmax. Oh, I think we can use that. We're looking for Vmax. What do we have? VRMS. Root 2 is root 2. Nothing to do about that. So VRMS equal to what? Vmax over root 2. Please write the formula. I'll be finishing now. V what? RMS equals to what? Vmax over square root of 2. Do we know VRMS? What is it? 230. I need calculators right now. Over what? Root 2. This is over 1. What do we do? Cross multiply. Vmax is what? 230 times root 2. What is your answer? 325, 27. And what's the unit? Volts. Guys, check. 1 mark for the formula, 1 mark for substitution. There, you have your 3 marks in the bag. Done. Make a note of what you have. Okay. Can we go to the next question? That's so simple. We're done. Number 2. Calculate what? RMS current. What are we looking for? IRMS. So we are looking for IRMS. IRMS. Easy. Let's walk through IRMS together. Again, go to your formula page. We are looking for IRMS. Check, what do we have? We've got power. We've got VRMS. We're looking for what? IRMS. I think I've seen my formula already. We've got power. We have VRMS. What are we looking for? Check. Come on. No one should get this wrong. What do we have? P average equals to what? V RMS multiplied by, do we know power? Let's walk through quickly. My power is 2,000. Do we know VRMS? VRMS is what? 230. And we are looking for IRMS. What do we do? Divide both sides by what? So what's the answer? 8,70 amps. Check again. You have your 3 marks. 1, 2, 3. Aha. Easy. Look at the last question. What are you looking for? The resistance of the appliance. But if I go to this formula, do you notice there's no resistance here? Where's my formula page? Check. Oh, there's actually, yeah. Do you see that? Please look up. We're finishing now. That's why I said, if you make a list of the things you have and just run to your formula page, life becomes easy. I'm looking for resistance. What do you see? P equals to what? I squared R. But what type of I? RMS. I could also use this one. P equals to what? V squared what? RMS. I could also use Ohm's law. Do you know Ohm's law 1? Where V equals to what? IR. The only thing is, if this is RMS, this must also be RMS. So you can use any of them. Let's just use one. P equals to I squared what? R. Please take note. Don't make mistake. There's a difference between RMS and max. P average equals to what? I squared RMS multiplied by resistance. What is my power? 2,000. What is the current? Remember, it's RMS. Oh, simple math. What do we do? Divide both sides by what? 8,70 squared. What is your answer? 20? Did you square it? Again, check your marks. Formula, substitution. Guys, I want you to check 9 marks. Check 9 marks. All by making a list, using your formula page, substitute, and do your basic math. You're done. It's fine. Your answer, if you use V squared RMS, your answer will just be a little bit different. Do you know why? Yeah, it's just maybe 4, 2, 4, 3. And it's because we rounded off somewhere. The 8,70 was rounded off. Yeah, so that really, you are given the leeway to get that decimal. All right, guys, I am done. I hope I was able to deal with. Yes, Biggie? Sorry? IRMS. Yes. Amperes. That's the unit of current. Current is measured in amps. Quantity of charge. Coulombs. Electrostatics. Coulombs. Electrostatics. All right, guys. I hope you got 1 or 2 things there. Please just practice 1 or 2 questions again from here. And then make sure this is well sealed. Is that okay? Just practice sharp. This thing doesn't take long. Our next sessions, I'm sure you are on one of the groups, you'll get to find our next session and enjoy as we prepare for paper 1. All right? Good. Good night, everybody. Logging out. This is Crazy Physics. Oh, you're welcome, Palisa. You're welcome, Yusuf. Ashley, sweet. On all your groups, there are lovely Ziad. Thank you. All right. On all the groups, there are flyers on the classes. You'll get more information just tonight on how to join us for the other preparations. Good night, everybody, and thank you for watching. Bye, Taz. Goodbye, goodbye, goodbye.